let's say that we have a ramp that looks something like this. And then there is a horizontal track on which there is a circle, a circular path in a sense. So it comes like this, and then we meet our horizontal track once more, and it continues however it wants to continue. And we have a block here, let's say, with mass m. We are going to release this block at a height of h. We are given that the radius of the circle is r, and we are asked the question, what should h be in terms of r, such that our block can complete this circle, okay? So it will travel, and it will be here at some point, then it is going to travel in a circle. So for it to be able to travel in the circle, what should the height be, and what is the minimum height, of course? Because if you release it from a very, very high point, well, then of course it is going to be able to complete the circular track, because it will have lots of energy. But we are interested in the minimum h. So min h for completing the circle. Okay, this is the question that we are asked. How should we approach this question? Well, to approach this, I will consider 2 points. The first one is going to be point A, which is the point of release. And the second point is going to be named B, which is the highest point of our circular track, okay? Now, if we assume that there is no friction, and let's say that we assume no friction, that's what we assume. If there is no friction, then energy at A should equal the energy at B. Alright, this is by the conservation of mechanical energy. So, what is the energy that we have at point A? It is going to be all potential energy, and it is a special type of potential energy. It is gravitational potential energy near the surface of the Earth. And we have a formula for it, which I derived in a previous video. You can find it from the cards right now, also from the descriptions part. And that formula is mgh. Perhaps you know this formula but don't know the derivation. Well, then I highly recommend that you go ahead and watch that video from the cards or from the descriptions part. It is a very useful proof to be able to do. So we got this. And what about EB? And by the way, the reason that we only have potential energy at A is because we release the block. So there is no kinetic energy. Okay? Initial velocity is 0, thus no kinetic energy initially. What about the energy at B? Well, certainly there will be some potential energy. And let's say this even. We choose this horizontal track level as our y equals 0 line. This is the level that we choose as 0. What is the height of B relative to this horizontal line? It is just going to be r plus r. So 2r basically, right? The diameter of the circle, or 2 times the radius of the circle. So the height is 2r. Then we have mg. We will write 2r like this. But to make it more elegant, more beautiful, I put the 2 forward and then put the r. Okay? This is the potential energy. But we will have also a kinetic energy, because if our block is to complete the circle, if it is to turn from B, well then it should be moving. If it isn't moving at that point, if it isn't moving to the left, well then it is going to it is going to be accelerated straight down due to gravity, and it is going to fall straight down. So for it to complete the track, it should be moving to the left. It should have a velocity. So we have a kinetic energy term, which is in the form 1/2 mass times the velocity squared. And this isn't any velocity. This is the velocity at point B. Great. Here we see a great thing. We see that masses cancel. Yay, masses cancel. And we are getting very close to the end, because we realize we have h, r, and only other thing that we need to get rid of is velocity at b. So if we can somehow substitute for it, we will be done. And to substitute for velocity at point B, the speed actually, we need to use circular motion ideas. And to do that, let's draw a free body diagram for our object when it is at point B. Free body diagram at B. We will have our object represented as a dot. mg is going to be straight downward, the gravitational force, and then there will be another force that is normal force. It is pushing, it is a push by the track on our block, so it is downwards. And all of this will create an acceleration like this. And since we are given, since we know that the block will be traveling in a circle, at least that is the case that we're interested in, for it to be able to do that. So if we take it that it completes the circle, then it should have a special type of acceleration, which is called centripetal acceleration. Okay? So if we have then the sum of all the forces, and let's take downwards as positive here. So we have mg plus n is equal to mass times acceleration, which is centripetal in this case. And this comes from Newton's second law of this equation, which you can access the derivation of that from the cards right now, also from the descriptions part. Okay? So we got this from Newton's second law. We just added the forces to get the net force, and it is equal to mass times the acceleration. Acceleration in this case is the centripetal acceleration. And it turns out that we have a formula for centripetal acceleration, which I already did write in a previous video. You can find it from the cards, also from the descriptions part. So we have mg plus n is equal to m, and using the formula that I derived for centripetal acceleration, it will be vb squared divided by r. Alright, and you should be happy at this point because we have vb. We want to substitute for it, so maybe we should solve for it, but hold on a second, we have n. I don't like this. Why do we have n? And I mean, how can we solve for n? It seems like there is no way that we could find a formula for n. But in fact, we don't need to do that, because remember, we are interested in the minimum h case. So what is the minimum height that we need so that our block makes it through the circle? It needs to make it barely, okay? This means when we come to point B, our block will be at the edge of falling, since we are interested in the minimum h case, okay? So we say minimum h. For minimum h, we will have mg, but n this time will go to 0. Because as I said, for the minimum case, our block is just at the edge of falling. It isn't going to be able to complete the circle. It is just at the limit, and when that happens, n is 0, because normal force is a force of contact. If the contact is about to be lost, well then n should be very small, and in the limit, in the ideal case, it is 0. This is equal to mvb squared divided by r. Alright, and here we see that m's cancel, yay! So if we solve for vb squared, we multiply both sides by r to get gr. Cool. And what is left to do? Well, only thing that is left is substituting it. We then have, and we substitute it here, we then have gh plus 2gr. I meant to say equals here. Okay. So we have a plus, and for vb squared, we have gr divided by 2. And we see another cancellation. Hold on a second. G's cancel as well. Wow. What does this mean? This means that if we were to carry out this experiment on the moon or in any other planet, we would get the same answer. I think this is very interesting to know that if I were to do this in my home and if I were to do this on the moon, I would get the same result. It is very fascinating. And also, I didn't mention it, but since m's cancelled, it also means that the mass doesn't matter, so a heavy object and a a lighter object gives the same result, but I think the cancellation of the G is more impressive. So we got this, and now we are very close to the end. Look at this. We have H is equal to 2R plus R over 2. And if we solve for R, we then get 5 over 2R. And this is a special kind of H. This is H min. So we just show that if H is greater than or equal to 5 over 2R, then the block will complete the circle. And how did I arrive at this inequality? Well, I said I found the minimum case. That's where the equals come from. And we know that H is going to be greater than or equal to 5 over 2R, because if we release it from a very high point, it will have a huge energy, and it will easily complete the circle. Okay, that's how I was able to arrive at this inequality. Anyways, I hope this video was helpful. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care.